So without further ado, let's begin today's presentation. Today's topic is Jayhawk BTDA, an epoxy curing agent for high TG powder coatings. And we're very fortunate to have two speakers today. So let's begin by welcoming Dr. Vinay Mishra, Technical Development Manager at CABB's Jayhawk Fine Chemicals business. Dr. Mishra has over 20 years of industry experience through various leadership roles at ITW, Sika, Air Products, and Dixie Chemical. We also have Mr. Kevin Biller, President of Powder Coating Research Group. Kevin has been formulating and manufacturing powder coating since 1978. And in addition to PCRG, he is a regular contributor to Powder Coated Tough magazine, the Focus on Powder Coatings newsletter, the Ask Joe Powder column and podcast, and the instructor of the formulating course, The PC Kitchen. Kevin doesn't have a lot of free time, I see. Gentlemen, thank you, and the floor is yours. Please begin.
Thank you, Boris. Hi, this is Vinay, and Kevin and I are really grateful that you took the time from your day to listen to us and what we have to share. It looks like the results of the poll are here. So it appears the majority of the folks in the attendance today are either formulators or people who are involved with testing or designing of the powder coatings, and that's great. And then there is some good chunk of people who are suppliers to the powder coating industry. So this is great, just the right kind of audience. So let me close my little poll window. So just a quick introduction about our companies. I'll begin with Jayhawk, which is over 50 years into, it's got more than 50 years of experience, history. We've been based in Southeast Kansas from the beginning. And now we are part of CABB, as Boris mentioned, and we've had other company corporate ownerships. Most recently, Evonik owned us for about 20 years. One half of our business is custom manufacturing and fine chemical production. And the other half is what we are discussing here today, which is the designing and production of dianhydrides. And we are a global leader in the applications for the dianhydrides into the thermoset polymers. Kevin?
Yes, hi my powder coating friends, and thanks for joining us. For those of you who are not familiar with what I do in the Powder Coating Research Group, it's my latest venture, which I started back in 2007. So we're celebrating our 14th year as an independent laboratory. We obviously, by this presentation, you can tell we work with raw material suppliers, advanced material people. We do services for powder coating manufacturers. We kind of have a global base of customers. We also work with OEMs in either troubleshooting or, in some cases, developing specific technology for their needs. So we're located in sunny Columbus, Ohio. Not too sunny, but anyway, I'm very pleased to be joining Vinay in this presentation. We did the powder coating end of the evaluation, and we kind of partnered on doing this work. So look forward to sharing it with you.
Great, thanks, Kevin. Before we start showing you the results of our study that we did together, Kevin and I would like to go over some of the basic stuff, just so we are all on the same page. So let's cover what dianhydrides really are. We are obviously going to talk about BTDA, benzophenone tetracarboxylic dianhydride today, but that's just one of many commercial dianhydrides that are important to the thermoset industry. 3 are shown as an example on this slide. It is safe to say that most dianhydrides, if not all of them other than BTDA, are almost exclusively used in polyimide applications. But BTDA is a rather versatile dianhydride because it finds uses in polyimides as well as epoxy applications. It has a melting point of about 225 Celsius, and it's most commonly used in a powder form. So the workhorse for the industry is what we call BTDA, polymer fine powder, that has a median particle size of 10 to 22 microns. And that is the grade we did use in this study as well. There are some customers, some applications that find it is better to have a finer particle size. And for them, we do produce what we call BTDA microfine, which takes down the median particle size to 2 to 5 microns. Kevin, anything you want to add?
One thing I want to mention to those that are familiar with powder coating processing technology, and as you probably know, our mixing step or our paint making step is compounding using a melt mix extruder. And as you can see here, the melt point of the material that we evaluated here is around 225 Celsius. It's very common to compound powder coatings closer to 100 to maybe 125 degrees Celsius. And this largely has to do with the behavior, the melt viscosity, and rheology of the base resin that's part of the binder of the powder coating formulation. So in this case, it's important to know we're dispersing a powder curing agent, in this case, obviously BTDA, but during the processing, it was a dispersion of relatively fine particles into the mix, and just keep that in mind.
Perfect.
Thanks,
good point. Let's take a quick look on the chemistry of these kinds of systems. So a die anhydride like BTDA will cure any epoxy compound. Obviously, it's just looking for the epoxide functional group. Now, many other curing agents can give you high performance, but for them to give you high performance and high cross-link densities, they actually need to have a epoxy resin also of high functionality to begin with. Epoxy Novolac resin would be one example, where some curing agents will give you high performance using the high functionality type resins. What's different about BTDA is that a formulator can choose BTDA and use it with a standard bisphenol A-based solid epoxy resin, simple dye functional epoxy resin, and you can get high performance, very high degree of cross-linking from that system, just because the BTDA works in it differently. And also, we should have a second poll at this point so we know what kind of applications are of interest to you guys. Maybe you can bring that up. I think this poll should give you a multiple choice. You can select more than one apply. So please hit submit after your selection. Kevin, anything you want to add on the epoxy resins?
Yeah, and for the basis of this exercise that we did, we kind of stuck with the standard BPA type resins. We wanted to build a baseline of information and data, and some of these things we have listed on this page. It's just kind of a guideline that there will be reactivity with these materials. We're not saying that in all cases it's practical. As you're getting into things like GMA acrylics and TGIC, you got a whole bunch of cross-link density going on there. But we wanted to make the point, if these are present in a formulation or they could be present, it's just something to be aware of.
Yeah, perfect. All right, let's see if, sometimes takes more than a click. Oh, we have the results of the poll. All right, this is great. So most respondents are interested in either heat resistance, be it thermooxidative stability or just general heat resistance, or corrosion resistance. So that's great. And then significant chemical resistance in electrical insulation. Yeah, so all of these are performance criteria that BTDA-based epoxy formulations can satisfy. So great. Thank you for your feedback there. Very quick look on the chemistry of the epoxy anhydride curing. So generally it is accepted that there is a two-step reaction process for the cross-linking between an epoxy resin and an anhydride functional curing agent. We have reaction 1 and reaction 2 here, showing that two-step cross-linking reaction. And then reaction 3 is simply the epoxy resin homopolymerizing with the help of some impurities or other things, but it can take place, this homopolymerization reaction can take place in the absence of the dianhydride. And this reaction is actually quite important for us to understand. Sometimes it hurts our performance, but in many cases, we believe a formulator can cleverly design some, or I should say pre-engineer some amount of homopolymerization into your formulation, and that can get you actually better performance than otherwise.
You know, there's something to note here too. You know, as formulators, with powder coatings, there are a number of curing systems that we work with that are pretty straightforward. And because of that, it's pretty easy to just say, okay, we're going to go one-to-one stoichiometry, you know, make sure all the functional groups, all the reactive groups are accounted for, and we're going to get the best performance. I think with Vinay's pointing out here, this is a little different than just straightforward, you know, singular type, you know, cure mechanism. And because of that, you'll see in the upcoming slides, because of that, we really had to take a look at stoichiometry and say, what are we going to do about that? And you'll see in our evaluation how we handled that.
Yeah, exactly. So, you know, the art of formulation really comes into play in BTDA-based epoxy formulations. And like Kevin has hinted, we did have to go off stoichiometry, if you will, in order to get better results. And we know from our historical experience that our customer base also uses far more off-ratio formulations for these kinds of systems. So basically, at the bottom, there is an equation. Different people calculate the usage rates of curing agents in different ways. I mean, this is one way. And just to give you an idea, if you have 100 grams of your chosen epoxy resin with a defined EEW that you know from the supplier, and you have the equivalent rate of 161 for BTDA, then this equation will give you the amount of BTDA to use in the formulation for 100 grams of epoxy resin, PHR sometimes we say. And there is this important fudge factor, or I guess artistic calculator factor that we use, which is the A/E ratio in the formulation. And that is the anhydride equivalents divided by the epoxide equivalents. So it's the ratio in the formulation of the anhydride to epoxides. Now, if you look at just the cross-linking reaction, not the homopolymerization, just the cross-linking reaction, you will see that one epoxide group will be equivalent to an epoxide group, and that normally tells you to use 1-to-1 ratio and epoxy AE ratio 1, but you get far better results by going anhydride starved and epoxy excess in these formulations.
You know, another thing to mention here, Vinay, is that you know, we've got a lot of functionality here. You know, when you see that, you know, the anhydride opens up, and you know, during the curing process, you know, it's a very dynamic situation where you're going to start consuming functional groups. You're going to have chemical reactions right away, and what can happen, you know, we kind of know through experience, and you can do this analytically as well, but there comes a point where you have steric effects and diffusion effects where you just can't get those functional groups back together because you've already built a pretty high molecular weight network. So that's another factor when looking at, you know, formulating these types of materials. It's like, you know, we got to look outside just the one-to-one stoichiometry.
Exactly. So basically, between the issue of vitrification, which Kevin, you mentioned, and then on top of that, you have the issue that BTDA, by its very nature, will cross-link a resin to a very high degree, or it would have, at least have the potential to cross-link to a very high degree should vitrification not occur. And if you did complete all those reactions, you can have what we will call over cross-linking. You may have a very tightly bound network, which doesn't have the physicals your coating needs. So for that reason also, it's best to go way off ratio, and we'll give you some examples of how much we're talking about. And that way, the excess epoxide that is in the system will have a chance to homopolymerize and consume itself, and your system will be better optimized that way. So here's the next slide, which we use to give an example of what kinds of stoichiometric ratios to use for different kinds of resins. Obviously, the shorter the epoxy resin molecule, the shorter the equivalent weight, the more off ratio you will have to go, basically more anhydride starved you'd have to go. So in most cases for powder coatings, if you're using EEWs of 500 to 700, 900, we'll say go instead of 1.0, use 0.6, 0.7, 0.8, those kinds of ranges. And basically, again, what we're saying is if you calculate by pure stoichiometry, you get an amount of anhydride to use with your resin. But we're saying use 60% of that or 70 or 80% of that for your epoxy resin.
There's another thing that I can add here. You know, as formulators, you know, we look into our formulating toolkit, and you know, we try to achieve a balance of, you know, performance features, and it could be chemical resistance, it could be, you know, heat resistance, it could be flexibility, elongation properties, you know, it could be, you know, thermal cycling type behavior. And the way we set this up, we wanted to look at a survey of different equivalent weight, which translated into different molecular weight epoxies, just to see the response and see where these things fit in. Because with formulation, it's like you know, cooking soup, or you're making a nice sauce or something. A little bit of this, a little bit of that, and you look for the balance of performance. And what we try to do here is, you know, determine the fundamental performance with different molecular weights, so that a formulator could see that and incorporate it into the needs that they need for their formulation.
Well said, Kevin. Just a quick reminder, please do send the questions in by chat to the host. And of course, if you have any quick question that you need, maybe it helps clarify something, just put in the word quick question in there, and then we'll try to take it as we go as well. We can make it as interactive as possible given our virtual arrangement here. So once again, when properly engineered, a BTDA epoxy powder coating formulation will have the ability to provide very good thermoset properties, such as heat resistance, thermooxidative stability, electrical performance for sustained periods of time. Can you imagine an electric motor running for years on end? It has to just work. There should be no failure on the electrical insulation properties there. It's a testament to this kind of a system. And then, of course, barrier properties because of its high cross-link density. So barrier properties to water, to chemicals, for pipe coatings and things like that. No surprise that these kinds of systems have had a track record of over 30 years of applications in coating powders for electrical motors, bus bars, electrical encapsulation molding powders, and of course, fusion bonded epoxy for larger surfaces like pipe and rebar. So we wanted to do a little research study to systematically try to understand and work with up-to-date commercial resin systems that are available these days, and try to understand what happens to the properties of these kinds of systems based on formulation variables and cure processes. For the properties, we decided to focus on just TG, glass transition temperature. We figured that's a good indicator of the extent of cure that occurs, of course, temperature resistance, and cross-link density. And many of these properties would be affected by the cross-link density. So we just focused on the high TG or TG measurement. We had support from lots of entities, but most importantly, powder coating research group. Kevin, would you like to describe your team there and how you helped us out?
Okay. Yeah. I just want to acknowledge, you know, our team. our guys in the lab, there's Nick Page, our kind of testing manager, and then there's a gentleman named Nathan Biller. Biller seems to be a very common name in Columbus, but yeah, he's does most of the formulating. He did, the formulations, and they both did the processing studies. They work as a very good tag team. So, thanks to those guys for producing the results.
Absolutely. Yeah, appreciate Nick and Nathan there. And another person I want to mention is Mr. Nikola Bilic. He's a research associate at the Kansas Polymer Research Center, and that's part of the Pitt State University in Kansas, not too far from where Jayhawk sits. So Nikola helped us out with the TG measurements and some of the DSC analysis of our uncured powders as well. Last but not least, Dr. Lin Young Hee of Olin Corporation helped us out with epoxy resin samples for the study and some valuable advice. And Dr. Pritesh Patel of Evonik helped us out with the samples of the imidazole accelerator for the study. Kevin, want to describe our formulation selections, please?
Yeah, and I mentioned we have a survey of different molecular weight, different equivalent weight bisphenol A type epoxy resins. Kind of the about as low as you can go. You go a little bit lower than this, but the lowest melt viscosity is going to be around a 2.5 type, and it's basically for storage stability issues. But yeah, we started with a 2.5 type, very common in the industry. 4 type, it's a workhorse, especially for functional type coatings, where relatively high film builds are necessary. And then we also did, I wouldn't say an outlier, but it's about as high as we go in molecular weight. It's a 7 type, and with this molecule, you're going to be looking at a fairly high molecular weight. These things have 2 functional groups, and yeah, we just wanted to get a good idea how BTDA behaves in those types of systems. So each one of those were done in separate formulation studies. They weren't mixed together. Just for clarity.
Right. Yeah, and I remember, Kevin, you were advising me that the 7 type, the DER667, usually is used as a modifier in a broader mix of epoxy resins in a formulation. Mm-hmm. I remember being very, very greedy and academic, wanted to understand how just that resin works. we found out that it is better suited for modifier for a modifier purpose, which you were saying all along. And then I think you covered it, but just in case, the A over E ratios, the anhydride to epoxide equivalent ratios that we used, 0.5, 0.6, 0.7, 0.8. And most of the data we'll actually start to see 0.678, because 0.5 was a little too low for these kinds of systems, which we kind of knew, but we still included that anyway. But 0.6, 0.7, 0.8 were more along the lines of what we needed to do. Go ahead, Kevin.
Yeah, people that are familiar with powder coating formulating, these are fairly boilerplate type of formulations. You can see the the binder, the resins, of course, on the top. BTDA is our curing agent. We kept the catalyst level at a constant level, and then we got some very common, further raw materials and additives. We like to keep things simple so that you can see the effect of the part of the formulation that you're evaluating. So we've got a very common flow agent. It's a polyacrylate, very, very common degassing agent, and then just a kind of standard grade chloride process rutile. Titanium dioxide that's been treated for dispersion and for UV resistance, although UV is not important here. But anyway, the formulations are very, very straightforward. And then, we did our extruding with a twin screw. You see a little picture of it there. A co-rotating 500 RPM twin screw. It's of the Baker Perkins vintage or design, which is very common in the industry. The barrel temperature, we varied depending on the melt point of, or the melt viscosity, I should say, of the primary resin. So the 2.5 type we looked at 100, essentially 100 degrees C. The 4 type, we bumped it up about 10 more degrees. And then the 7 type was extruded at 130 degrees C. And the whole point there is just to have a good, the right kind of viscosity going through this compounding step. So the material was fed, like I mentioned, the RPM set at 500. Material then goes through chill rolls, and those familiar with powder coatings understand this. Chill rolls, and then that stuff is broken up into flakes, and then in the upper right-hand corner, that's what the powder looks. After it's been processed. Don't try to take that through an airport. But anyway, that's how we made our samples.
I don't know if I changed the slides too quickly, but we did, the spraying, Kevin, you guys did on Q panels, and then cured the panels for 20 minutes at 200 Celsius.
Yeah, we picked just a very standard curing system, or a curing condition, and we'll see as things go on. You and your team, Vinay, did some pretty interesting thermoanalytical work that went beyond that 200 degrees C cure condition.
Right. So actually, that's exactly what happened. We just wanted a simple 20-minute 200 C type conventional cure cycle, just so we know what we get from there. And then we started building different kinds of cure cycles. But now here you have the DSC results, and you start seeing work from Nicola Billick at the Kansas Polymer Research Center. So the bottom curve, the black curve, is the DSC thermogram showing a TG of about 109 Celsius. And that's from an actual panel that was taken from Kevin's lab. And it was cured, so we just chipped off a little piece of that cured coating and put it in the DSC to get this. So we got this TG of 109. All right. And then we also had a lot of uncured powder of the formulation. So that's where we started doing some crazy stuff ourselves. But before we went crazy, we wanted to just reproduce what was done in that last sample. So what we did was, for this red curve or brown curve, we took the uncured powder, cured it for 20 minutes at 200 C within the DSC itself, and then scanned it to get this brown TG scan. And we got basically more or less the same TG. You have a residual exotherm at the high temperature. So very good reproducibility between a large scale oven cured system and a tiny DSC system. Then we wanted to see what happens if we raise the cure temperature. Now we did that 2 different ways. In one case, we just did 20 minutes isothermal in DSC cure, but instead of 200 C, we did it at 250 C. So there is really no difference except the 50 degrees C bump on this. And then another experiment we did where we took the uncured powder and just continuously heated all the way to 300 Celsius. So basically ramp cured in the DSC. And let's see what we got for the 2 curves that way. So when we did the isothermal, same kind of a thing as the brown curve, just going up from 200 C to 250 C. The TG we got was 126 Celsius, a nice little bump. And then when we took the uncured powder and just ramp cured it, not really isothermally, but just relatively fast ramp all the way to 300 and cooled down and tested the TG, we got 122 Celsius. I would say more or less the same, but what it told us was that the 20 minutes was probably more important than the 5 minutes it got over 250. Then we wanted to do one more crazy experiment. We said, okay, we're going to go back to 200 Celsius for cure. We're not going to go over 200 C, just stay 200, but leave it at 200 for curing for a long period of time. And with long, we said, all right, 24 hours, that way we don't have any question. We let it cure for 24 hours and then scanned it at the in the DSC. And this is what we get. A really nice bump, 155C. Now remember, the blue curve and the black curve, the only difference is that one is cured for 20 minutes and the other is cured for 24 minutes. So there's sufficient, to Kevin's point, the system was sort of vitrified where it needed more time for the linkages to come in contact with each other to build cross-link density further. So the system had the capability to build the cross-linking further, but just needed more time. This was very interesting to us.
You know, there's something I could pitch in here. You know, when you run an experiment, and people that work in a lab, they know you don't get all the answers from your first experiment. And what the experiment usually does, the data that you generate, you get more questions. And not that you're not getting answers, but it begs other questions. And you know, as we go through this, you know, there's a question, okay, why do we still have residual cure? There could be a question in solubility. You know, how soluble is the BTDA at different temperatures and with different resins? That's one question that kind of crossed my mind. The other thing, you know, going back to like the third or fourth slide, the particle size may have an influence on cure response. And this is, you know, just something that needs to be answered.
Yes, exactly.
So we don't have all the answers here. We're presenting what we did in our experiments and our characterization work, but yeah, go carry on, Vinay.
That's a very good point, and it hits right home as to why some of our customers prefer the finer particle size, the BTDA microfine grade, and that there may be some of these issues are tied together. Excellent point. So again, the key thing is that, you know, this was one particular formulation out of those 12 formulations you saw in that table. Here's the 2.5 type epoxy resin, 700 equivalent weight, and one particular stoichiometric ratio, A over E. But you know, everything you see here is just difference in curing profile. So obviously we saw that the TG is substantially increased from the original simple 20-minute cure cycle. From 109 to 155. That's pretty good deal, actually. And then the other thing we notice is that when properly cured, these systems will have a relatively faint glass transition, not only high, but very faint. In fact, this was the case for most of our formulations from the study. When these formulations were cured for 24 hours at 200C, some of the other formulations didn't even give us a DSC TG. This is the range we expected, and we didn't see the TGs. So we knew that we had to do DMA tests to be able to at least make out the TG when you cure it to that extent. And we did do that. But before we go to the DMA, just want to show that this issue of TG suppression is well known in the industry and well known in the academia. So this is an example of some acrylic acid polymer where it shows that in a DSC, the TG will keep going higher and higher as you increase the level of cross-linker in the polymer. And the TG also becomes more and more suppressed to the point that at this fourth level here, the TG cannot even be discerned by DSC. Same thing that we noticed. And what we believe this is a very good testament to why BTDA-based epoxy coatings have a cult-like following in some of the formulation world, because not everybody fully takes time to understand what goes on behind the scenes in the molecules, but people know that they give you good performance and good properties. And we believe this issue of TG suppression may very well have something to do with why these systems are used in some of the more challenging applications.
There's another thing to mention here, Vinay. You know, if we're talking about heat resistance in particular, and we're talking about, you know, in the field performance, because that's where the rubber hits, you know, meets the road. There is precedence with with a few powder coating chemistries where further advancement of, T sub G, further network development happens in service, especially for, high heat applications where, it's something is going to have, relatively continuous high heat for long periods of time. And the coating, it's pretty darn good when it gets into the field, like when first is put into service, but within, hours, it's significantly better.
Yes.
And the practical part of that, and this is important from a commercial standpoint, the coating's good, it's put on, but it meets its final performance after a few hours in service, and that's not unprecedented. So
yes.
Keep, we're not asking people to, okay, well, we'll tell your customer to cure the powder at 24 hours at 200 C. That would be very impractical. So anyway,
yes, that's an excellent point. That bring the coating to a functional level of cure so that the part can be handled and put into service, but then it will cure further before the full force of the service environment takes place.
Hey guys, this is Boris. I just want to chime in for a second, let you know we're at 37 minutes. We're getting questions coming in, but I'm going to hold them until the end so you guys can complete your remarks, and then we'll go into the Q&A.
Thank you, Boris. We'll speed up a little bit so we have more time for questions.
Yeah, we only have 100 more slides.
We never told you. Kevin and I are nerds. We love data.
Oh, sorry.
Sorry.
We'll get moving.
So just to show you, we didn't have a chance to do DMA testing on all the specimens because we had, by the time you take the powder and make the coupons, but Nicola Billick really did some great work preparing specimens from the powders that we had. And here's a series of the same resin that we've been seeing, the 700 equivalent resin, that, if you have the AORE ratio of 0.6, 0.7, and 0.8, your TG starts going up from 134C to 164 and 170. And I think you recognize that some of these TGs we couldn't detect by DSC. So it is nice to actually see that, you can actually get 170 Celsius TG. And we did have confirmation of that particular data from DSC actually. Actually, that one gave a little bit higher, but more or less DSC and DMA did give us good correlation, at least in the situation where we were able to detect a TG. So that was a good thing. At least the conditions worked out. And you can obviously see that the TG rises steadily if you increase the amount of BTDA or the AORE ratio down by the bottom here. Now, the 24-hour cure, we could not get the TG out of every DSC run. So we couldn't compare all of those formulations in that way. And we didn't have the DMA results for all of the formulations. So we said, all right, forget the 24-hour cure stuff. But just look at the other curing techniques that Nicola ran in his DSC. So here you have the 20 minutes at 200C and 20 minutes at 250C, and then the RAM cure to 300C. So no matter which condition you look at, you can see a steady increase in TG as the A/E ratio, the stoichiometric ratio is increased. So more BTDA thrown in, the more TG you get, more cross-linking you get, makes sense. And that happens for both the resins shown in this chart. And then, of course, if you compare broadly this 700 equivalent weight data and with the 900, you can see that the TGs are slightly lower for the 900 resin, which makes sense that you have, this is a shorter resin molecule. When you go to 900, the space between the epoxides increases within the structure of the resin. So you have overall reduced cross-link density in the three-dimensional network. So that makes sense. And this coating is not necessarily worse. It could be the right coating for that application because you may need that little bit of taking that edge off of the rigidity that a larger molecular weight will give you. So we just have a few conclusions that we were fortunately able to get some relatively contemporary resins from the industry, from Olin, our friends at Olin, and get high TGs using the simple solid epoxy resins based on bisphenol A. And with this 4 type resin, we could get in the 170 Celsius range relatively easily. And in addition to getting the high TGs, we also noticed that when you cure these things in the right way, you can get TG suppression as well, which of course limits, which of course tells you that it's got a high cross-link density, but more importantly, that the TG suppression indicates that the properties of the coating would not change dramatically as the material is heated through the glass transition temperature itself. A lot of times that becomes a threshold. You don't want to push the product beyond the TG because the properties would change drastically. But in this case, this may be the secret why BTDA epoxy coatings are so popular in many applications, because you can possibly expect that these formulations can take an overload every now and then for a short duration of time without completely catastrophically failing. Kevin, your thoughts?
Okay, yeah, from a formulator's perspective, I look at, coming up with a product for a customer requirement as dipping into my toolbox and using, whatever appropriate tools are needed to get the correct, balance of performance, mechanical performance, chemical performance, maybe heat, certainly cost, performance balance. And, if there's one takeaway that I want to leave with, our powder coating friends is, this is another tool to put in your toolbox. And, we've demonstrated, the kind of fundamental behavior of BTDA with the pretty straightforward epoxy type resins. And you can see the behavior and how you can navigate into getting higher T sub Gs for sure. We didn't do a lot of other testing. We know that higher TGs are going to give you, certain performance features that kind of go along with it, heat resistance, chemical resistance, and things like that. Maybe a loss in mechanical performance like flexibility and elongation, but at the same time more hardness and abrasion resistance. So what I just want to say is, this is something to consider when you need to navigate into higher performance type coatings. It's a technique that can be used in formulating.
Very, very good point, Kevin. Well, that brings us to the end of the slide. I don't know where the 100 slides are, Kevin, that you and I had prepared.
I don't. I'm going to have to look through my files.
Well, thank you all for your attention, and I hope we have some questions, but keep in mind as the questions come in, take the information down for Kevin and I if you want to reach us out later, and we can address any questions afterwards too, but let's take some live questions now.
Hey, thanks, Vinay. So I'd like to thank both of you for your nice presentation today. Obviously, I'd like to thank our audience for staying on for now what will be a lively Q&A session. So we'll use the remaining time to have our speakers respond to the questions submitted by you, the audience, and we have quite a number here, so let's get started. First up, this is very intriguing. This takes you back to slide 20 when you spoke about the different cure conditions. And the question is, did you look at degree of cure, percent cure for any of these varying conditions that you have discussed here? What about degree of cure is the question.
That's a very good question. And actually, we did look at the residual cure exotherms. And as you can see, the bottom curve, the black one here, there's a significant residual exotherm. And so we were monitoring those things. What happened was after a little bit of changes, we started not being able to get that residual exotherm. Look at this pink curve, there's nothing here. And the green one, there's nothing here. So we couldn't detect how much more exotherm could have come out. And this is frankly what was really surprised, that this curve looks like there is nothing left to cure, and yet when we allowed the curing to occur more, it bumped up the TG and suppressed the TG too. So we were not able to, beyond a certain point, we were not able to do the analysis of residual cure exotherms.
You know, there's another just real quick thing. I'm not a polymer physicist. I'll give you that disclaimer right up front. But when I've posed this to polymer physicists and say, hey, you know, is this thing still moving? They'll say, okay, it's not going to be something that you can quantitatively measure with kinetic type analysis, but it could be morphological. And then it's like, well, okay, you know, but you know, realistically, there may be, you know, morphological changes that are starting to move the T sub G, you know, independent of residual cure, you know, incompleteness of cure. Just something to tuck away. Anyway.
Yeah, and that's a more eloquent way of saying what I did. I think.
Oh, I don't think so.
What we think was happening is that there's certainly chemical reactions taking place, some bonds are taking place, but perhaps some bonds are getting further strengthened. Some cross-links are getting more thermodynamically more optimized in order to boost the TG further and further and suppressing the transition itself. But overall, the magnitude of those reactions from a thermal energy release is very hard to predict, at least using these experiments.
Good, guys. Thank you. The next question is kind of related. Let's see, it's basically to say you've more or less established 250C in order to fully cure these systems out. So the question is, what about a thermal degradation temperature? Do you have any remarks about that? Was TGA, for example, considered here, where you could talk about the end of the spectrum?
That's interesting. And the short answer is we did not get to that yet. It is on our next round of studies. At Pitt State University, we are doing some additional work on BTDA epoxy systems to determine the thermal degradation temperatures of fully cured systems. We believe they will be certainly, 300C or above, because we have been testing up to 300C already in this scan, and we're not seeing really crazy, stuff breaking up at this point. But we will definitely have that, and look out for a follow-up webinar, hopefully before the end of this year.
Great, thanks, Vinay. Another question speaks to rheology and kinetics, so-called rheokinetics. Have you had an opportunity to consider those type of properties of these BTDA epoxy coatings?
Kevin,
No, that's a great point. And really, when you look at, the behavior of thermosetting materials, in my world, it's thermosetting powder coatings. We coined the phrase, not me, but industry coined the phrase chemorheology, because it is dynamic. And one of the biggest problems we had, and I would see it with this, but I'm not saying it can't be done, is, we look at things like cone and plate type rheometers, hot stage cone and plate rheometers. And you could look, it used to be you'd look at, rotational type viscosity measurements. And then people said you could do oscillatory or, oscillations and get really good, data. And then you'd fuse the instrument, so you almost have to have a disposable instrument, because something like this may be fused so hard that it'd be impossible to disengage things. And as a young chemist, I remember going to the rheology labs, and they're going like, "You better not mess up my $50,000 rheometer."
Yeah, right.
But that being said, this is place this in the hands of a very good polymer physicist, and say, thermoanalytical type experts, and say, hey, you guys, we'd like to take this, to that level. And I gotta believe, since I was a young formulator, things have progressed significantly.
Yes.
And there's got to be, it's a technique, it's an instrumentation thing, because theoretically it makes all the sense in the world to follow chemorheology, on any thermosetting system.
Yeah, and Kevin, if I may add, yes, actually to your point, the instrumentation has been updated, and they do offer disposable test plates for those rheometers these days, and I've used them too, except that this system we haven't had a chance to look at that yet. We may consider that. I think the problem is this system is so dynamic. It starts out as a solid at room temperature. Then as you're going to heat it, it'll melt, viscosity will decrease, and you're going to start testing it at that point. And then it is reacting, and we think there's just too much happening, and we think it'll be a little bit hard to understand what's going on with the data. But haven't totally given up on that idea. But first, we want to focus on the curing and the TG measurements and some mechanical behavior. Eventually, chemorheology is definitely on the radar for us to work on. Probably not happening this year, but I promise you next year we'll talk about that.
Thanks, guys. Yeah, my chemorheology experience is pretty stale. It's about 30 years old, so I can't really add to the discussion. But I remember how important it was, especially if you want to do some modeling experiments. So yeah, very good question. Thank you for that one to the participant. So another question going in a different direction about mechanical properties, stress strain. Can you tie this high degree of TG to rigidity, brittleness, and have you considered that?
The short answer is yes, we have considered that. We haven't had a chance to test those kinds of properties yet. The idea is to first narrow down what kind of formulations and what kind of TG performance that we are going after and what kind of cure profile that are good candidates, and then hone in with those formulations, those cure profiles, etc., and to start doing mechanical property measurements. They do take some extra time for sample preparation. Of course, Kevin, you and your team will have to make us a lot more powder in order to make mechanical testing coupons. So that's kind of the reason why we haven't started that yet. But that also is in the near future for plans.
And from my perspective as a formulator and a coatings kind of evaluator, commercializer guy, over laboratory test panels, your cold rolled steel, thin gauge type test panels, stuff, these higher T sub G things, especially, they're going to be pretty brittle. But when you get into the realm of functional coatings, and a lot of times they're put on some very heavy, dense substrates. Like if you think of potable water, like a valve casting, valve castings that have valves in them and things like that. The testing protocols change, and we do some of that work in our lab when we venture into this kind of area. But we would be putting things over 1/4 inch or 1/2 inch steel, and then measuring elongation properties or slow deformation and things like that. Traditional polyester powder coatings, you put it on a thin test panel, you coat it, you cure it, and then you hit it with 160 inch-pounds. In the case of these materials, the vitrification, performance and stuff or mechanism, it's going to make these things pretty brittle, and that's where you may have to balance, more higher molecular weight materials in them if you need to move in that direction. So
right.
Kind of a long-winded answer, but yeah.
Yeah, and that's why we wanted to do different molecular weight, different EEW resins. So this repeating unit N that you see, we just need to nail down as to which of these resin structures would be more ideal for different types of coatings.
Thanks, guys. We're nearing the end of the presentation, so I'm going to finish with one more question, which has been covered elsewhere, but I think it's important here for you guys to comment just to close out today's talk, and that's about the topic of accelerators. Talk about which type of accelerators work well with BTDA epoxy resin formulations, and keep in mind we've got a few minutes left, so whatever remarks you add to.
Let me see, I think I might have had a backup slide. Let me see if I can find it. Yeah, there you go. not all of these catalysts that you see are conducive to powder coating because some of them are actually liquids. But we have previously at CABB, we've previously done some studies using the same catalyst that we used in this study, the 2-methylimidazole, and also 2-phenyl-4-methylimidazole. So you could say we tried imidazoles a lot. And then we also tried a urea catalyst. And so we've done work with many different types. We've also done work with amines, but because they're liquids, we didn't choose them here. There are some other chemistries besides amines, imidazoles, and ureas that we know work with dianhydrides. And literally just as we speak, Nikola is opening up a package in Pitt State University with a bunch of new catalysts that we have identified for some resin epoxy, resin BTDA studies, some completely different chemistries. And so we'll have a lot more understanding of what's going on. And that I think actually will be our next webinar, possibly as early as summer. There are many catalysts that we know from, how can I say, just by through literature, we just know that people have used BTDA with those accelerators. So if you have specific interests, we can definitely guide you in addition to whatever you see on the screen. Kevin, anything you want to add? I mean, you've been around, you've seen BTDA being used.
Around, yeah, I've been around so long I forget what I did. But some of the things in the past, like Lewis acids, onium type chemistry sometimes works. And I'm not talking necessarily about anhydrides, but I'm talking about, driving, ring opening epoxide, oxirane opener, whatever. But there's kind of a laundry list. The powder coating industry really likes the imidazoles, and there's, there's a long list of imidazoles and, different molecular weights, different solubilities,
different temperature activations,
all of that stuff.
Yes.
And it's good stuff. I'm trying to think of quaternary ammonium compounds, sometimes, stuff along those lines. And it just seems like we come back to the imidazoles usually. But, that being said, if you're looking at some pretty specific curing conditions and stuff like that, I think, yeah, it bears, it's valid to be looking at, a number of different types, rather than just a family of, things like imidazoles.
Right. Since, Kevin, you brought up quaternary ammonium salts, actually that is one of the catalysts that we are just starting to study at Pitt State with Nikola.
Okay, thanks guys. Yeah, we're just coming up on the hour, so this concludes today's presentation.